So I would like to find a basis for a vector space, but for that to happen, I'm gonna need a list of vectors, and they need to span the vector space, and they need to be linearly independent. But we also knew that for a set of vectors to span, the rank of the matrix has to equal to m, so I need the rank to equal to m. But for my vectors to be linearly independent, I'm also gonna need the rank to be equal to n. So I need these two conditions to hold, but what that means is the rank of the matrix has to equal to m and n at the same time. So in the end, whenever I have a basis for a vector space, I'm gonna need m and n to be equal, and that has to equal to the rank of the matrix A that I have here. And we also have talked about the dimension, which is the number of vectors in a basis, and we have seen that the basis for R squared has two vectors, so this guy has dimension 2, and that makes sense. Whenever I have a basis for r to the m, they will always have m vectors, so r to the m will always have dimension m. So for this next example, I'd like to see whether these guys form a basis for r cubed. So in this case, my vectors here, they are going to be in r cubed. The value for my m is going to be 3. So if they form a basis, what that means is the value for n need to be 3. So I'm going to need n equal to 3 vectors. So in the case that I do not have 3 vectors, then I can rule that out right away, that they are not going to be a basis for R cubed for sure. Now then, when they have 3 vectors, I have to do the computation, but for part C, I can see that this is basically just the standard basis for R cubed. So this guy is indeed a basis for R cubed. If I were to put this into a matrix and find the rank of the matrix is going to be 3. Now then, for part D and E, we actually have found the rank of the matrix that we can get by putting these vectors together already. This is for example in example 1.7. The rank of the matrix from part D is going to be 2, and the rank of the matrix from part E is going to be 3. So the one from part E will form a basis for R cubed. Notice that the basis for a vector space is not unique, so the 3 vectors from part C, they form a basis for R cubed. The 3 vectors from part E, these guys also form a basis for R cubed. Yeah, so there are many possible choices for a basis. However, all choices will have the same number of vectors because R cubed has dimension 3. So whenever I have a basis, there will always be 3 vectors.